I'm going to record this session. Good
afternoon.
Hello. I'll send you this recording along with page numbers from the text that you may want to read with regard to chemistry, which is our topic for today.
And we got a test today, right?
Today you have a quiz.
I mean, quiz today.
And
Yeah, quiz.
some of you have taken it already. And you
we could go early.
You can go from midnight to midnight.
Okay.
And so just make sure that you get it done well before midnight tonight. Because the quiz goes off at exactly midnight.
12 o'clock.
Well, some of you have wondered if I actually read the things you say in chat. And the answer is yes, I do. But I don't do that until after the class period is over. So if you want to send me a message in chat, you can do that. And I will find it and respond to it after class.
What time does class end today?
Say that again.
What time does class end today?
Good point. It ends at 1:30. So it's only a 60-minute class today because you have a quiz that will take 15 minutes of your time. So who just spoke? I need to record this.
Oh, Yusuf Faraj.
Faraj, okay, I got you. And Yolanda, you have spoken.
I have a question, Professor.
Okay.
Yeah,
This is Sasha.
Sasha, okay.
For our test, Sasha Douglas.
Sasha Douglas, okay. All right.
For our test, do we get any study guides or anything like that? Or for our final, do we get a study guide?
For the final, yeah, I may send out something for you to focus on. By and large, that's the function of the homework assignments, whether they're graded or ungraded. The idea of homework is to help you study. So I don't arrange specific things that you should look at. And usually, sometimes I do. Sometimes when I'm going through slides, I'll say, you should know this. And if I say that, then you should. But I don't like to be too directive, because if I tell you what to study, then that's all you will study at the expense of everything else. And I'd really like you to be familiar with all of the material that's presented.
Professor?
Yes.
You already got me down. I don't know if it would be extra credit or just info for you to know or to help with the class later or whatever. But if we find some stuff on the news or whatever that we think is interesting, like the other day I found something that says scientists identify massive ocean worlds that may host alien life. And I wanted to send you that article. Would that be extra credit or just info for you?
Well, I'd love to have it. It wouldn't be extra credit, but anything that you have you'd like to see discussed in class, I'd love to have it. And in fact, I do the same thing when I see an article in the media that I think is interesting and relevant to this class. I bring it up. I make it part of the slide set. So yeah, I appreciate that if you do.
Okay, thank you.
I do read chats. I want to also remind you that I have office hours. So at 2 o'clock on lecture days, Mondays and Wednesdays, at 2 o'clock, I'm on Zoom. And so if you log into Zoom, we can talk. Also, I sent you on Monday my record of your class participation, and I asked you to correct it. Some of you have responded, and I have corrected the record according to what you said. And if I don't hear from you, then I assume that the record I have is correct.
Wait, where did you post this?
I sent it as an announcement, I think on Monday.
Yeah,
Okay.
It's a spreadsheet.
Professor, next Monday we have class.
No, we do not have class next Monday. So this is Rasha.
Yeah.
Okay. No class. So we won't see each other again until a week from today, next Wednesday.
Professor,
Yes.
did you like do a date for the test or not yet? For the first test?
The first, I haven't set a date for it. I will set that soon because I want it to be after the next section. So today we're doing chemistry, and then we're going to do biomolecules and molecular molecules. And after that, I'd like to have test one. But I haven't set the date yet because I never know how long it's going to take to get through a slide set.
Professor, can you change the dates on the modules? Because some of them are dated February 2021, and that's so long ago.
Yeah, that's confusing. So, but
It
it makes
is.
a good point that always check the date because those dates from spring were from last semester, spring semester. And they're,
Please fix that. I'm so confused.
okay, you'd like to see them all deleted? I can do that.
Well, yeah, fix the date to the right date, not just delete it. No.
Well, no, I can do one of two things with things left over from last semester. I can either update them or I can delete them and put in the updated version instead.
Yeah, that's better. Okay. Thank you.
Okay. I'll do that. All right, we have a lot to go through today. So I'm going to share my screen with you. And you should see basic chemistry for biology. Let me know if you can't see that.
Yes, I can.
Okay. Why do biologists need to understand chemistry? It's a good question. Well, all life is composed of matter, and matter has mass. It occupies space. Living things are made up of molecules that are produced by chemical reactions. So reactants are converted to products. So here's something for you to think about at the bottom. Any life form, from single cells to complex humans, is nothing but a collection of chemical reactions. So each of us is nothing but the sum total of all the reactants in our bodies that are being converted to products.
Quick question of curiosity. This is Anthony Emilo, but is there people who, I suppose yes, but is there people who map all the chemical reactions in the human body? Like, do we know all of them yet of everything, or do we just have a very good idea about a lot of them maybe?
We don't know all of them. There are so many, there are literally thousands.
Yeah.
So we don't know all of them, but the ones we do know are those involved with particular processes like digestion of food. We know a lot of the reactants and a lot of the products involved in digestion, for example.
Gotcha. Thank you.
Well, let's start with atoms. Atoms are the smallest components that an element can be broken into by ordinary chemical means. Now, we are made of the same stuff as stars. Here's a video you can watch. I'm not going to show that in class, but when the universe began, that is at the time of the Big Bang, about, depending on who you listen to, 13 billion years ago, the atoms were all mostly hydrogen. And over time, within stars, the hydrogen atoms fused into helium atoms, and they in turn, again over a long amount of time, got converted into heavier elements like carbon and oxygen. Then these were released into the universe when stars exploded, so that our planet Earth is composed of materials that started out as hydrogen atoms and has ended up as organic molecules. Now, a material, well, what is an element? It's a material made of only one type of atom. And each element is represented by a chemical symbol, like C for carbon, H for hydrogen, and so on. And all of the elements that are known are organized into a chart called a periodic table. So here's an example of a periodic table. So there are 94 naturally occurring elements and a lot more that do not occur naturally. And approximately 25 of the elements in this table are essential for life. But the main ones I've circled in red. So remember this: CHON, C-H-O-N, carbon, hydrogen, oxygen, and nitrogen. So let's look at one box in the periodic table. If we go back to cobalt, it's number 27 here, cobalt, and here is an expanded view. So each little box contains critical information. The atomic name, in this case it's cobalt, the chemical symbol, which is CO, capital C, small o, the atomic number, 27, the atomic weight, 58.9, and the electron configuration over here on the right, 2, 8, 15, and 2. So what do all these things mean? Just to re-emphasize, the major elements in organisms are these 4, and they make up about 95% of the mass of an organism. Then there are minor elements that make up less than 1%. You see them listed here. And then there are the so-called trace elements, again listed here. We need trace elements in very small quantities, and they make up less than 0.01% of the total mass. Why do we need them? For various functions, and here are some examples. Calcium for bones and teeth, magnesium is a cofactor for enzymes, we'll talk about that later. Iron is in hemoglobin. Sulfur is critical for the function of proteins. Copper is necessary for hemoglobin. Potassium for our nerves. So these are just some examples of why we need them. We don't need much of most of them, but if we don't have any, we suffer. Now, how do we get these things into our bodies? We eat them. Sometimes with supplements, sometimes a disease will interfere with absorption of nutrients. So here's a label of a vitamin supplement. And you can see that there are a lot of different vitamins and minerals in certain vitamin supplements. So what are atoms made of? 3 particles. And at this point, I'd like to show you a clip from a TV show. This TV show was called WKRP in Cincinnati. It was on the air between 1978 and 1982, so it's quite dated. It's about a gang member. So many of you probably were not even born when this show was on TV, but it's kind of interesting to see how they handled atoms.
I hated that show.
Excuse me?
I hated that show.
You heard of it? Well,
I hated it too. I didn't like it.
well, I don't know if you like this or not, but
Okay.
try.
I can give you the basics of the atom in 2 minutes. You'll understand it perfectly and remember it for months. 2 minutes? You're crazy, you know that? I can teach you about the atom in 2 minutes. Will you go back to school and finish out the year? How about it, huh? Come on, you're a betting man. How about it, Arnold? Yeah. Yeah, okay, sure. You got it. I got your word? Yeah, you got my word. In 2 minutes. We got a deal. Yeah, we got a deal. All right, sit down. There are 3 gangs on the street, right? Yeah, 3 gangs. And this right here is the territory. Now, here is a neighborhood. Got that? Yeah. And right in the middle of this neighborhood is a gang called the New Boys. Yeah, the New Boys. Good name. Okay. Out here on the outside of the neighborhood, on the edge of the neighborhood, is another gang. You know, these are real negative dudes, really negative, right? Right. Now, they call themselves the elected ones. All right, the elected. You got that? Really negative. They don't like nothing. Right. Now, they all the time out here circling around the neighborhood, just circling, you know, checking out the New Boys. Now, the New Boys see this, and they get, you know, they figure there's something wrong here, so they make a deal with another gang, a gang of very happy-go-lucky guys. They call themselves the Pros. Pros. Now, the Pros are very positive cats. See, they got all the good-looking women, right? Yeah. See, now the Pros and the elected ones, interesting thing, they hate each other. So much so that they keep the same number of members in the gang, just in case you did. Right. So if I got 10 elected ones, how many Pros do I have? 10. All right. Now, how many gangs do I have? 3. Name it. The New Boys, the elected ones, and the Pros. All right. Who's here? The elected ones. All right. Now, what are they, negative? Yeah, negative. All right. Now, who's positive? The Pros, and you running out of time. All right. Now, you see right here, the Pros and the New Boys, they call their hangout the nucleus. Yeah. Now, see, that's a real tough word. It's Latin. I kind of think it's Swahili, and it means center. Yeah. What is it? It's nucleus. Say it. Nucleus. Is that really African? Say it. Nucleus. You got it? Yeah. All right. Give you another Swahili word. It's a tron. It means dude. Yeah, tron, dude. All these gangs like that name so well that they all decide to use it. For instance, the Pros right here, you're gonna start calling themselves protons. And the New Boys, they start calling themselves neutrons. And out here on the edge here, the electric ones, they start calling themselves the electrons, the protons, and the neutrons. And all this right here, this is the neighborhood. This is block after block, nothing. You understand block after block, nothing. Yeah, I know all about that. And your time is up, Professor DJ. Yeah, I was finished anyway. Now you going back to school. School? Man, all I know about is a bunch of damn gangs that live in a brown neighborhood. That's the atom. That's it, man. That's it. What's this right here? Protons and neutrons. All right, they call this the what? Nucleus. All right, what are these guys up here? Electrons. Are they negative or positive? Negative. And how do they move? Round and round. And if I got two of them, how many protons do I have? Two. Now, protons negative or positive? Positive. All right, and what's all this right here? Oh, that's the negative. Which is? Nothing. You got it, man. You get an A.
Professor,
Yeah,
those cats were too cool for me.
yeah. Well, I don't know how cool they are these days, but I guess they were pretty cool in the 1970s.
But that's cool how he put it in something he can relate to understand.
Yeah, it may or may not be useful to you, but I thought it was kind of funny, and I thought at the very least you'd find it amusing.
It was interesting.
All right, are we back to composition of atoms? Everybody see that?
Yes, I can see.
Yes.
Okay. All right, we're going to talk about the composition of atoms. And as you just saw in the video, they're made of protons, which are positively charged, neutrons, which have no charge, and electrons, which are negatively charged. The protons and neutrons, the yellow balls and the green balls, are in the center, in the nucleus. The electrons are outside the nucleus. They are the purple balls. Now, this is an analogy between an atom and a solar system. So here we have an atom of sodium with the nucleus in the center and electrons going around the edge, and they're moving. So the question is, what keeps them in their orbits? Because each electron has an orbit to which it is assigned. Well, the forces involved here are, first of all, the electrons are negative, the nucleus is positive. So there is an electrostatic force that's attracting the electron to the nucleus. So why doesn't it just smash into the nucleus? Because it's moving and it has a centrifugal force. So the centrifugal force is throwing the electron away from the nucleus. And it's the balance of those two forces, electromagnetic and centrifugal, that keeps an electron in its orbit. The same thing happens in a solar system. So here you see our sun, here is our planet, and all the other planets, and they're circling around the sun. Each of them is attracted to the sun because of gravity. The sun has a very large mass, and so each planet is pulled toward the sun by the force of gravity. So why doesn't it just crash into the sun? Again, because of centrifugal force. So the centrifugal force on any planet is equal to the gravitational force that's attracting it to the sun. And that's what keeps each planet in our solar system in its orbit. So I show you this just to give you a sense of how things can be similar, going from very small like an atom to very large like a solar system.
Professor, I have a question.
Yeah, Lopez.
Yes, Diego Lopez. So we know that the neutrons are neutral and protons are positive. Do you know what keeps them together?
The neutrons and protons, what keeps them together? I presume it's a gravitational force, but I don't know that. I'm just
Okay, so
guessing.
it's not like scientifically.
They both, see, the point here would be that both neutrons and protons have mass, and anything that has mass has a gravitational field. And so they're attracted to each other. Now, electrons have no mass, and so gravitation does not come into play with electrons. So let's go through this. What are protons? They're positive, they're in the nucleus. Now, these numbers that we're going to go through next are important. So the number of protons is equal to the atomic number. So if you look at a box, in this case, cobalt, on the periodic table, and you see the atomic number is 27. That means cobalt has 27 protons. So let's go further to neutrons. Neutrons are found in the nucleus. Also, the number of protons plus the number of neutrons is equal to the atomic weight. So if you look at the atomic weight for cobalt, it's 58.9, we'll call it 59. And when you look at the atomic number, that's the number of protons, 27. So to find out the number of neutrons, you take the atomic weight, which is 59, the number of protons, subtract the number of protons, and you get the number of neutrons, which would be 32. So is that clear? How you, first of all, find out the number of protons, and then from that and knowledge of the atomic weight, you can determine the number of neutrons. Now, the number of electrons equals the number of protons in a neutral atom. In other words, with a neutral charge, the number of electrons is always equal to the number of protons. So you know the number of protons from the atomic number. And so you immediately know the number of electrons. The electrons are distributed in shells or orbitals at specific distances. And I've told you why or how these distances are determined. What is an isotope? It has the same number of protons and electrons, but a different number of neutrons. So if the question of isotopes ever comes up, just remember they have a different number of neutrons. So electron orbitals. Each orbital has a maximum number of electrons that it can hold at any one time. The first shell of any atom, and this is true of any atom, has two. So there's a nucleus, first shell has 2 electrons. The second shell can have a maximum of 8. So here, again, you see the nucleus, first shell with 2, second shell with 8. The most stable condition for an atom is when its outermost shell is filled with electrons. If it isn't filled, then that atom becomes reactive. So we have here some examples of reactive and unreactive atoms. So if you look at this illustration here to the right, on the left side of it, you find the reactive atoms, hydrogen, carbon, and sodium, because each of them has an unfilled shell. So hydrogen has just one electron. It wants two. If you've ever, well, hydrogen can become more stable by forming helium. So helium has two electrons in its outermost shell, and it's very stable. In fact, helium is inert. Similarly, carbon only has 4 electrons in its outermost shell. So it is highly reactive, and that's why life is carbon-based, because carbon can form compounds with almost anything that isn't inert. If the outermost shell is filled, you have neon, again, an inert gas. Sodium is a really interesting one because it has 8 electrons on its second orbital, and it has a third orbital with just 1 electron. So it is extremely reactive. If you've ever dropped a bit of sodium metal into a beaker of water, you know what happens. It essentially explodes. Argon, on the other hand, its third shell is completely filled with 8 electrons, and it is another inert gas. So atoms in living systems, you have hydrogen. These are the 4 most abundant compounds in living things: hydrogen, carbon, nitrogen, and oxygen. You can see they're all reactive. Hydrogen wants 1 electron. Carbon wants 4. Nitrogen wants 3 to fill its outer shell. And oxygen wants 2. So they're all trying to become stable by filling their outer shells. And this brings us to the issue of bonds. So bonds is how atoms fill their outer shells and become stable. Atoms with unfilled outer shells become more stable by acquiring or sharing electrons from other atoms. This can happen when a chemical bond is formed between 2 atoms. So there are 3 types of bonds. I put a red circle around this because I want you to remember it. It'll be coming up over and over as we go through the course. So there are ionic bonds. Ionic because ions are formed that have opposite charge that attract each other. And these bonds are strong. Covalent bonds, I've underlined the word share. So keep in mind that a covalent bond shares electrons. So the 2 atoms that are sharing electrons have formed a covalent bond. And this bond is very strong. That's what holds us all together. Organic compounds are largely covalent bonds. And then there are hydrogen bonds, which are nothing but an electrostatic attraction between a hydrogen and a polar molecule. And hydrogen bonds are weak. It's very important that you remember that hydrogen bonds are weak. It's critical for biology. So this shows a covalent bond where you have 2 hydrogen atoms, each one looking for another electron. They find another one in another hydrogen molecule, a hydrogen atom, and they make a hydrogen molecule. So let's talk about ionic bonds. So this is how one forms. One atom transfers an electron to another atom. If it loses an electron, what happens to it? An electron is negative. So if an atom loses a negative charge, it becomes, somebody tell me, it becomes positive. So now it's a positive ion. Now there's another atom that receives an electron. And so if it receives an electron, which is negative, now this recipient atom is going to have a negative charge. So now we end up with two ions, one positive, one negative, and they attract each other, and this is an ionic bond. Ionic bonds are most common when an atom's outermost orbitals contain just one or two electrons. So if they have just one, they need to give that up is the easiest thing to do. If they need just one, the easiest thing is to accept one from another atom. A good way to illustrate an ionic bond is with salt, sodium chloride. We have a sodium atom that has just one electron in its outer shell, making it very unstable. We have a chlorine atom which has 7 electrons in its outer shell, which makes it unstable. So sodium wants to give up an electron, chlorine wants to gain one. So as soon as sodium gives up an electron, it becomes a positively charged ion. And as soon as chlorine accepts an electron, which is negative, it becomes a negatively charged ion. So these two ions, being of opposite charge, they attract each other, and that's what forms the ionic bond. And this just shows the same thing in a different form. Here's an ionic compound. This is a crystal of salt. You can see the sodium ions and the chlorine ions all attracted to each other through ionic bonds. Now, what about covalent bonds? Remember I said covalent bonds are very strong. They're really the basis of life. And they form when two atoms share electrons. So one or more pairs, I've underlined pairs, covalent bonds always form due to pairs of electrons. So pairs of electrons can be shared. And here's a very simple example of a covalent bond. Again, we have two hydrogen atoms, each with just one electron. If they each share their electron with another hydrogen atom, they form a hydrogen molecule. So they're very unhappy if they only have one. If they're sharing, they each have two. So a single covalent bond can be represented either with a molecular formula, H2, or with a structural formula, which shows the single bond itself. And you see that here, it's just the same thing illustrated again. This is how you write it out. A hydrogen molecule is either H2 or H bond H. Now, there can also be double or even triple covalent bonds. So the number of single covalent bonds an atom can form is equal to the number of additional electrons needed to fill its outer shell. So here you have two atoms. They each have 6 electrons in their outer shell. If they share 2 pairs of electrons, now they're happy because they each have 8. This happens to be oxygen. Oxygen has 6 electrons in its outer shell, 8 electrons total. And so you would write that out. An oxygen molecule is O2 or O double bond O. This would be the structural formula. This would be the molecular formula. And this just shows the same thing. Oxygen molecule O2 has a double covalent bond. We've just gone over that. A nitrogen molecule, N2, has a triple covalent bond. And that happens because nitrogen has 5 electrons in its outer shell. So it's looking for 3. So it'll share 3 of its electrons with another nitrogen atom that has 3 that it wants to share. So now you have a triple covalent bond. Now, examples of covalent bonds. We've gone over these hydrogen molecules, H2, oxygen molecules, O2. Here's methane, which hydrogen bonds covalently with carbon. And so since carbon wants 4 electrons and each hydrogen atom has 1, it takes 4 hydrogen atoms to satisfy carbon, and you get the gas methane. And here, methane, the molecular formula is CH4, the structural formula is here. And then there's water. We have oxygen with 6 electrons in its outer shell. It wants 2 more, so it gets 2 atoms of hydrogen. Now the hydrogen atoms are satisfied because they each have 2, and the oxygen molecule is satisfied because it has 8. H2O is the molecular formula for water, and the structural formula is O bond H bond H. So this brings us to what types of chemical formulas are there? There are a number of different types, but there's only 3 that I want you to remember. I've already talked about molecular formulas and structural formulas. Molecular formulas give the actual number of atoms in the element of a single molecule. So a single molecule of methane is CH4. A single molecule of glucose is C6H12O6. The structural formula for those, with a single bond, it's H bond H, double bond is O, double bond O. Methane has 4 single bonds. And here's a structural formula, not a complete one, a structural formula for glucose. And you can see this is very different from the molecular formula of glucose. Now, empirical formulas are used less often, but they are the simplest ratio of the number of elements in a compound. So you get the empirical formula by dividing the molecular formula by the lowest common denominator. So if we take glucose here, lowest common denominator is 6. So we divide by 6. 6 into 6 goes once, into 12 goes twice, and into 6 goes once. So the empirical formula for glucose is CH2O. How do we write chemical formulas? The subscript is the number of atoms. Subscript is the number of atoms. So you see examples here. O with a subscript of 2 means that there are 2 oxygen atoms. CH4 with a subscript of 4 means that there are 4 hydrogen atoms. H2O, H has a subscript of 2, which means there are 2 hydrogen atoms and 1 oxygen. And here's glucose, 6 carbons, 12 hydrogens, 6 oxygens. So the subscript determines the number or indicates the number of atoms. The preceding number, preceding to the formula, is the number of molecules. So if there is no number, like you see here, the number is 1. If there is a number, that indicates the number of molecules. So 3CH4 would be 3 molecules of methane, 12H2O, 12 molecules of water, and 7 C6H12O6, so 7 molecules of glucose. So we have 2 things to remember here. If there's a number in front of the symbol, it indicates the number of molecules. The subscript indicates the number of atoms.
So let's say if you gave us a test on that, you want us to write them out as it did on the previous screen slide. You want us to write them out like the O and then slash the O to be 2002, like that.
Yeah, if I asked you to write the molecular formula for oxygen, you'd write O subscript 2.
Okay.
Or if I ask you how many molecules are represented in 12H2O, you'd say 12.
Okay, to actually write them out, like the little O's and then put the little hyphens, with the
Yeah,
little H
if
on
you're
them,
asked
like
to
that.
write them out, make sure you get the subscripts correct and,
Okay.
and the number of molecules correct.
Okay. Thank you.
Professor, this is Alicia Carroll.
Uh-huh.
Is this going to be on our quiz today, or is this going to be on our next quiz?
Next one.
Okay, thank you.
Hallelujah.
Did someone have a question? Because we're going to go on now to polar and nonpolar covalent bonds. So when electrons are shared equally between atoms in a molecule, the molecule is nonpolar. Nonpolar molecules are hydrophobic because they won't dissolve in water. But when electron positions are skewed to one side of the molecule, that molecule is polar. And that's what I want to illustrate here. So here's a water molecule which is polar. You can see that there are more plus charges on one side. The hydrogen atoms are on one side of the oxygen molecule, which makes one side more positive and the other side more negative. Now, in contrast, a nonpolar covalent bond, and here in this case with methane, we have 4 of them. All the molecules are equal, all the electrons are equally distributed. So it's nonpolar. Similarly, with an oxygen molecule, the electrons are evenly distributed. If we look at the bottom illustration, a nonpolar covalent bond, you have electrons evenly on one side and the other. And an ionic bond, it's that the electrons are always equally distributed. But in a polar covalent bond, there's more electrons, more charges on one side of the molecule than on the other, and the other side has more of the opposite charge. So is that clear, the difference between a polar and a nonpolar? It all has to do with the distribution of electrons. And this is one of the questions on your homework. It asks you, I can't remember how it asks, but what it wants you to know is that in a polar bond, the electrons are distribution is skewed to one side. Polar covalent bonds. So this is a polar bond, covalent, and again, we're looking at a water molecule. So the oxygen atom has a negative charge on one side. The 2 hydrogen atoms each have a slight positive charge on the opposite side. So one side of the oxygen side of the molecule is slightly negative and the other side is slightly positive. This is pretty much the same thing that I just already told you. I have this in here so that you can read the legend here and perhaps get a better feel for what makes a polar molecule. And again, just a space filling model of a polar molecule, which in this case is water. So this brings us to hydrogen bonding. Hydrogen bonds are critical because they are probably the most abundant bond in living things. And without hydrogen bonds, there would not be living things. So what is it? It's the electrostatic attraction between a hydrogen atom in one polar molecule, for example, water, and an electronegative atom in another polar molecule. So it's an attraction between two polar molecules with the positive end of one attracted to the negative end of the other. Because oxygen, nitrogen, and hydrogen atoms are abundant in biological systems, hydrogen bonds are very common. And a point to be made here is that hydrogen bonds are weaker than covalent and ionic bonds. They're easily formed, also easily broken. And that's important. So just some examples of why the DNA double helix would be impossible without hydrogen bondings. Protein folding to give enzymatic activity would be impossible without hydrogen bondings. And the specific heat of water is high because of hydrogen bonding. If that was not true, water would boil at 80 centigrade instead of 100, and all the water on the planet would evaporate. So the reason we have liquid water on the surface of our planet is because of hydrogen bonds. So this is, I think, an easy to understand illustration of a hydrogen bond. Usually they're illustrated by dotted lines. So this dotted line here is a hydrogen bond between two water molecules. So the bond is between a hydrogen atom on one molecule, which has a slight plus charge, and it's bonded to an oxygen atom in another water molecule, which has a slight negative charge. So this is an electrostatic attraction, which forms a weak bond. So this illustrates the same thing, except there are more of them. There's several water molecules, and you can see in each case, the hydrogen is bonded to the oxygen. It's never anything else. It's always hydrogen bonded to an electronegative molecule.
Professor, I have a question.
Yeah, Priscilla?
Yeah. So for hydrogen bonds to form, they bond between like molecules, right? Not the other ones.
The hydrogen bonds form, what did you say?
Between molecules, not the, what are the other ones called?
Yeah, they form between atoms that are parts of molecules. So if you look at this illustration in front of us here, you see that each of those molecules composed of an orange ball and two white balls, each of those is a water molecule. And each one is hydrogen bonded to another water molecule.
Yeah, but what I was asking is that they bond between like molecules, not the atoms themselves.
Right. Yeah, you don't get hydrogen bonds between free atoms. It has to be part of a molecule. More water molecules. If you study this closely, you'll see that every water molecule is hydrogen bonded between an H and an O to every other water molecule. And it's this property of water, the fact that it can hydrogen bond to itself, which determines life on Earth. If it wasn't for hydrogen bonding, life on Earth wouldn't exist. So water is the most abundant substance on the Earth due to the special properties of hydrogen bonding. It covers 75% of the Earth's surface, and cells were up to 95% water. That is, the mass of most of us is water. And the substance, like compounds, are a minor part of our composition. Water is the only substance on Earth found naturally in all three states of matter. So water exists, it can exist as a solid, ice, as a liquid water, or as a gas, steam. It has a neutral pH. It's a universal solvent. It dissolves more substances than any other liquid. And it has a high specific heat, which means that it absorbs a lot of heat without changing temperature. So since the Earth is covered with so much water, it can take a lot of heat from the sun. It can be absorbed in all this water without changing the temperature of the planet.
Professor, this is Gabriela Galvez. I have a question. I have a question about that. You said that 75% of air surface is water, right?
Yeah.
So in California, we have a big dry problem. So we have no water, but we have the Pacific Ocean. Why there, I don't know, engineers of the people who's working on, bringing the waters, do something to get the water from the ocean. What is the big problem that we cannot get the water from our ocean?
The big problem is the need. So ocean water is not potable. It's salty, whereas we need fresh water. So desalinization plants can solve that problem, but desalinization plants are very inefficient. So they can take ocean water and make pure water out of it, but at a slow rate. So for example, in Carlsbad, near San Diego, there is a desalinization plant right on the beach. And it makes good water, but not nearly enough to satisfy the water needs of San Diego. So,
Professor.
And also, I'm sorry, and also have another question about that. For the fires, when we have the fire season, can we use the ocean water to use it for the fires or no?
In principle, yes. The problem with that is that, again, it's salty. And so if you dump ocean water on a fire, the salt remains in the soil. And plants don't do well in salty soil.
Oh, I got it. Thank you.
Anything
Sean,
else?
the other thing about desalination plants is they're also very costly. And from what I'm to understand, there are other drawbacks such as toxic brine that those plants produce, which are actually detrimental to the environment.
Right. So the brine, the salts that they take out of the water, they pump right back into the ocean. So in the immediate vicinity of the effluent, it kills everything.
Professor, this is Steve Stinson. The whole water problem, especially for California, it's definitely due to management issues, and that's one of the reasons why we suffer the droughts we do, is because we don't have a whole lot of reservoirs in this state necessary for the growth of the population.
Yeah, that's sort of an indirect effect. The direct effect is lack of rainfall. So we don't get, the last few years, we haven't gotten much rainfall. And in the mountains, we haven't gotten much snowfall. So the way the system is supposed to work is that we get a huge snowpack in the mountains, and then it melts slowly so that it percolates into streams and rivers and ultimately makes its way to the sea. The problem is, if we don't have much snowpack, coupled with the fact that the planet is warming, so the snowpack that we do get melts too fast. And so the water, instead of soaking into the soil, it just runs away.
So,
We're
Professor,
between the desert.
Yeah, this is Georgina.
yes. So the problem is because of global warming. Is that why it's so bad?
Yeah, global warming contributes to changing weather patterns. So as you probably know, there are some places that are getting way too much rain and other places that aren't getting nearly enough. And the Southwest of the United States is an example of the latter. We're not getting nearly enough. Now, San Diego gets most of its water, about 40% of its water, it gets from the Colorado River. And as you probably know, the Colorado River is drying up. It gets another 40% from the Sierra Nevada, from the snowpack. And as I just said, the snowpack is getting less and less every year. So the situation in the Southwest of North America is dire unless it starts raining again.
Professor, this is Anthony R.
Okay.
I'm not sure if you've heard about the artificial rain, like how they use in Dubai, but I think I was reading and they said they would use it here in California as well.
Artificial rain? I mean, like
yeah, it's like
cloud seeding?
Yeah, cloud seeding, exactly.
Yeah, that's something, that's a technology that's been tried for quite some time to try to get the water out of clouds and onto the ground. I'm not familiar with what all the problems are, but I know it's pretty inefficient with the technology that's available now. It's not, so far, it hasn't been shown to be the answer to our rainfall problem.
Professor,
Yeah.
since it's 1:30, am I allowed to leave?
Yes, if it's 1:30, everyone is allowed to leave, and I'll have to finish this slide set next time.
Have a nice day, Professor.
Okay, take care, everyone.
All right.
The end.
Thank you, Professor.
Thank you. Have a good weekend.
Okay, don't
Have a
remember.
good
Stay
Liberty.
safe. Stay safe
Bye.
out there.
Don't
Okay, bye-bye.
forget, Monday's a holiday, so we'll
Oh, yeah.
I'll
No
see you in a
problem,
week.
right?
Send an email. Send an email.
Okay. So see you Wednesday.
Okay, see you Wednesday.
Bye-bye. Best of luck on the test.
Art of talking.
Okay.
Professor,
Yeah.
I just have a question about the worksheet.